Dear students, in this paper of Organic Chemistry Part 2, the focus shall be on the reaction mechanism, and some of the reaction mechanism will take in the next paper. First of all, we will begin with the elementary idea about the various types of reaction mechanism. Already familiar with some of these mechanisms and how to tackle them, but we will have a review, and the initial two modules will be focusing on the various types of mechanism and how these take place with some examples. Then we shall discuss about the thermodynamic and the kinetic requirement, the kinetic and thermodynamic control and how it affects the course of the reaction, the Hammond's postulate and the various potential energy diagrams, the transition states and intermediates, what we mean by all of them. And we shall study the methods of determining the mechanisms, and we shall see how the isotope have important role in that. We shall also study the generation, structure, stability and reactivity of carbon ions, free radical, carbenes and nitrines. We shall also study the quantitative treatment with the Hammett equation and the linear free energy relationship and how the substituent and reaction constants will be affecting. Then we shall be studying all these mechanisms in detail one by one. So, the first focus will be on the aliphatic nucleophilic suction. As you are already aware, the aliphatic nucleophilic suction may be further of SN2 or SN1 or SNI, but we shall also go into SCT mechanisms and we will see how they can be mixed SN1 and SN2 reactions and how the various conditions like the solvents, the substrate, then you can have the effect that you can divert it towards more of SN2 or SN1. We shall also study another very important thing, which is neighboring group participation and how the enchimeric assistance happens with the pi and sigma bonds involved. We shall also study the classical and non-classical carbocations, the phenonium ions, the Nor-Bourneil systems, and we shall also study the common carbocation rearrangements. Some of this you are already familiar, but we will be going further into depth. The nucleophilic suction at allylic, aliphatic trigonal and vinylic carbon also will be emphasis in this paper. Further, we shall see how the effect of substrate, attacking nucleophile, leaving group and the reaction medium have impact on all these. After the aliphatic nucleophilic suction, then the focus will be on aliphatic electrophilic suction. And electrophilic aliphatic suction, there shall be focus on the bimolecular mechanism, that is SC2 and SCI. Then SC1 mechanism also we shall study, where electrophilic suction we shall study further how it is being accompanied by double bond shifts and how the effect of substrates, leaving group and solvent polarity is there on the reactivity in all these mechanisms. After the aliphatic electrophilic suction, then our focus will be on the aromatic electrophilic suction. You are already familiar with the aromatic electrophilic suction mechanism, but we shall be going into more details with some new examples that you have not studied earlier, where cyclic systems and polycyclic rings are being encountered. We shall see how the arenium ion mechanism takes place, how the orientation and reactivity and the various energy profile diagrams will be analyzed, and the ortho or para or ipso attack takes place and orientation in some other ring systems. We shall also see how the quantitative treatment of reactivity in substrates and electrophiles is done, and we shall discuss some named reactions like diazonium coupling, and we shall see how the diazonium coupling is utilized for the preparation of dyes and some of the indicators. We shall also study the Willsmere reaction, and Getterman-Koch reaction is used for the formylation of the aromatic ring system. And then we will be studying about the aromatic nucleophilic suction, and in aromatic nucleophilic suction we shall study the SNAR, SN1 and SRN1 mechanism and also the benzene mechanism. We shall see how the reactivity is affected by the substrate structure, the leaving group and the attacking nucleophile. And here we shall discuss some of the named reactions like von Richter reaction, the Somlet-Hauser reaction and the Smiles rearrangement. So dear students, this paper will give you a good understanding of all these various mechanisms with some of the examples that we will be dealing, and I am very sure that you will be able to all the further organic reactions with more understanding and clarity. So dear students, after the overview of the entire paper, let us focus on this module, and as I told you that all this that we will be studying in this module you are already familiar, but yes, it is very important to revise all these concepts. So here we shall study what are the various types of organic reactions, where we shall see what are the substitution reactions, what are the addition reactions, what are the elimination reactions, and recall that addition and elimination reactions are reverse of each other. We shall also see what are the rearrangement reactions, and then what are the oxidation and reduction reactions with some examples.
In this module, we will study the various types of reactions. After studying this module, we shall be able to differentiate between the different types of reactions and identify their type. By analyzing the reaction, we will also make out the difference between them. Organic reactions can be classified as substitution, addition, elimination, rearrangement, and oxidation reduction reactions. You are already familiar with these. Let us revisit these reactions to get an overview. Let us study substitution reaction first. Substitution reactions are those reactions which involve displacement of an atom or a group by another atom or group. Here, the substrate is attacked by an attacking reagent, leading to the formation of a product. Depending upon the attacking reagent, a substitution reaction can be nucleophilic, electrophilic, or a free radical reaction. You must be already familiar with the reaction of methane with chlorine in the presence of light. This reaction is an example of substitution reaction. Similarly, reaction of cyclohexane to produce chlorocyclohexane is also a substitution reaction. Notice that the hydrogen atom in the substrate is substituted by chlorine atom. It is a free radical substitution as the attacking species is a chlorine free radical. You must be knowing that nitration of benzene is an electrophilic substitution reaction. In this reaction, the hydrogen of the benzene ring is substituted by a nitro group. Other example includes bromination and sulfonation as shown here. During the substitution reaction, the geometry of the molecule is unaffected. Tetrahedral remains tetrahedral and planar remains planar. It is because an atom or group replaces the original one without changing the hybridization of the attached atom.
Let us consider some more examples, and we begin with the nucleophilic substitution reaction. Now in this, if we have a molecule where this is the cyclopentane ring and we have the substituents, and the stereochemistry is also depicted here. Now when this molecule is reacted with cyanide ion in the presence of alcoholic medium, what happens is we get this product. Now you can easily notice that this particular cyanide ion has replaced this Br and in turn the CN comes here. So this is clearly a substitution reaction, and because of this cyanide ion acting as a nucleophile, this is a nucleophilic suction. Another thing that you must be noticing here is the change in configuration. The Br was earlier placed here and now the CN has come here. It is just because this reaction proceeds via SN2, and there are other SN1 reactions where there will be racemization, and this will be discussing in detail in subsequent modules. Taking the case of electrophilic substitution, if we have this substituted phenol, that is, this is the metacresol, and when this is reacted with CH3COCl in the presence of AlCl3, the products obtained are and you can clearly see in these products that this COCH3 as electrophile attacks at ortho or para position, and subsequently you are getting the products where the COCH3 has come at these ortho and para position. So this is a electrophilic substitution where the hydrogens at these ortho or para positions have been substituted by the COCH3 group. Coming to the free radical substitution. In the free radical substitution, what happens is it is the free radical which will be attacking and replacing the other group or atom and giving you a substitution product. So if we consider the case of, say, cyclohexane, and if it is reacted with chlorine in the presence of sunlight, what happens is the hydrogen, it can be at any of these positions, all of them are equivalent, and this hydrogen will get replaced by the chlorine. And because here the chlorine attacks as a free radical, in the presence of sunlight there will be formation of Cl dot, which is chlorine free radical, and that is what is the first attacking species, and in turn hydrogen gets replaced by chlorine. So this is a free radical substitution reaction.
The next type of organic reaction is addition reaction. These reactions are characteristic of compounds containing multiple bonds. The alkene, alkyne, carbonyl, nitrile react by addition to the multiple bond. Addition reaction may be electrophilic, nucleophilic, free radical, or concerted. Recall that reaction of bromine with alkene is an electrophilic addition reaction involving the attack of electrophile and forming the cyclic bromonium ion intermediate. Reaction of aldehyde or ketone with hydrogen cyanide to form cyanohydrin is a nucleophilic addition reaction where cyanide ion is the attacking species. The reaction of alkene with hydrogen bromide in the presence of organic peroxide is a free radical addition reaction. Recall that bromine free radical attacks, in this case forming anti-Markovnikov's product as a major product via a more stable radical intermediate. Example of concerted addition reaction is hydroboration of alkene. Notice that simultaneous addition happens here. The resulting borane on hydrolysis gives alcohol. Addition reactions lead to change of geometry. In case of a double bond adding to give a single bond, planar geometry changes to tetrahedral geometry.
Let us now consider some addition reactions. And in the addition reaction, first of all, let us consider the electrophilic addition reactions. Now if we consider the case of this methyl cyclohexene, and if we do the reaction of this with HBr, then what happens is the H is positive, Br is negative. The first attacking species is the H plus, and this will attack in a manner so that there is a generation of more stable carbocation, that is at the tertiary position and not at the secondary position. So what we get as a result is the hydrogen has added here, and as a result we get this carbocation, and further it is then reacted with Br minus, and we have the formation of this. And you can clearly see here that this HBr has added to this particular double bond where H has come to this carbon and Br has come to this particular carbon. So this is addition, and because the first attacking species is an electrophile, that is why it is the electrophilic addition reaction. Now coming to the case of free radical addition, the same example we can take further, that is we have this methyl cyclohexene. Now if this is reacted with HBr in the presence of peroxides, what happens is these peroxides will break into RO dot and they will make the HBr generate Br dot, and this Br dot is the free radical here which is going to attack on the double bond at this position preferably, so as to give the free radical at this position which is more stable. So let us see what we get as a result. We have the formation of this radical as the intermediate, and further this on treatment with the remaining H dot which is there in the medium as ROH, it will take H dot and regenerate the RO dot. What we get is there is a addition of Br and H in this manner, and here this is free radical addition because the first attacking species is the free radical. And if we compare both the earlier and this one, the earlier was Markovnikov addition and this has happened via the anti-Markovnikov addition. We'll talk about this in more detail in subsequent modules. Moving to the nucleophilic addition. Nucleophilic addition is most common in carbonyl additions, that is when you have the aldehydes or ketones, and if you add a nucleophilic reagent, the nucleophile part attacks on the carbonyl carbon because it is electron deficient, oxygen is electron rich, and as a result what we have is the formation of this anion. The nucleophile has attacked here carbonyl and in turn these electrons move here, that is why you are getting this minus charge. Furthermore, the remaining positive part which here is hydrogen, and what we get is this nucleophilic addition. So you can clearly see here the reagent has added to this and this, where the first attack is of the nucleophile, that is why it is called as the nucleophilic addition. If you consider the case of an example, suppose we begin with this aldehyde and do the reaction with CH3MgBr. So this is an aldehyde and this is a Grignard reagent, and in this Grignard reagent this CH3 will be attacking at this carbonyl carbon, and as a result what we get is salt, which further on hydrolysis will give rise to the formation of this alcohol. So here again you can see this is an example of the nucleophilic addition where The Grignard reagent has added to an aldehyde and ketone, and subsequently on hydrolysis it is giving an alcohol. Consider the example of the fourth category of addition reaction, that is the concerted addition. First of all, what we mean by concerted means it is simultaneous. It is not one by one part of atom or group of the reagent which is adding and giving you intermediate, rather the entire molecule is adding. To understand this, let us consider the case of hydroboration. So when we start with this cyclohexene and it is reacted with BH3, there is a simultaneous addition of BH3, and that happens via a four-membered transition state. So how we can write? You can see here. So BH2 adds here and H adds here. In order to understand the concerted addition reaction, let us consider the case of hydroboration of this methyl cyclohexene. Now, when this is reacted with BH3, first of all, the boron being electron deficient and hydrogen here is as hydride, so the positive part attacks to that carbon, whereby it will be leading to the more stable carbocation at this position, and the hydrogens will be attacking here. So there is a concerted mechanism which takes place. Let us see how it takes place. So what we get is, it's already a hydrogen, and if we also consider the stereochemistry, the BH3 will be adding from same side. So this is the transition state which is formed, and ultimately it gets attached this way. We get H and BH2 added this way. Of course, this further on can be replaced by many substituents, like if you do the reaction with H2O2 in the presence of base, then we can replace this with OH, and as a result we have the formation of the corresponding alcohol, which is this. So this is again addition reaction, because this adding reagent has added to the double bond, but the two parts, that is the hydrogen and the BH2, have added simultaneously, and that is why it is the concerted addition. It is not part by part, that the H has added first and then the BH2, and in between there is an intermediate. So here there is no intermediate, unlike the carbocation or the carbanions or the free radicals that we have seen in other type of addition reaction. Here it is this transition state which is formed, and it further gives the addition product.
In elimination reactions, two atoms or groups attached to the carbon atom or atoms of the substrate molecule are eliminated. There are three types of elimination reactions, namely alpha, beta, and gamma eliminations. Let us see an example of each. Alpha elimination, also known as 1,1 elimination, is the reaction in which two groups are eliminated from the same carbon. Example: formation of carbene or nitrene. In the formation of carbene, as shown here, it can be seen that both the chlorine atoms are removed from the same carbon. On the other hand, dehydrohalogenation of alkyl halide in the presence of base to give alkenes is a beta elimination reaction. Here, both the atoms are eliminated from adjacent carbon atoms. In a gamma elimination, a three-membered ring is formed as shown here. A 1,3 elimination takes place in this case. Notice that in case of alpha and beta elimination reactions, tetrahedral geometry changes to planar geometry.
Now let us consider some example of beta elimination, which is the more common elimination. Now, if you take this methyl substituted cyclohexane and there is a bromo which is positioned on the cis side of this methyl, and when this is reacted with a base which is NaOCH3, the product that we obtained is this methyl cyclohexene, and there is a very minor composition of this, and this can be explained by the fact that here the OCH3 minus will act as a base and it is going to take out this hydrogen which is positioned anti to the Br. It will take this out, and as a result it will lead to the elimination of Br minus. So we get the double bond at this position, and why this hydrogen is preferred and why not the other hydrogen here, because this also, if you look, is in anti-positioning to this Br, and if this is taken out it will lead to the formation of this particular alkene. But out of this and this is a more substituted alkene which is more stable over this one which is less substituted and is less stable, and hence this more substituted alkene is the major product that we get here. But if we start with the trans isomer, that is the methyl and Br are now in trans position. Now what happens is, when this is reacted with the base NaOCH3, very interestingly the only product formed is this, and the other expected product, that is this one, is not formed at all. Now why this is happening is, if you consider the position of Br here, it is up, and the hydrogen at this position is also on the same side. So this elimination is a trans elimination, and H and Br, because of the same side, this hydrogen cannot be removed by this particular base which is OCH3 minus. On the other hand, if you look at the hydrogens here, we have this particular hydrogen which is anti or trans to this Br, and this OCH3 minus is going to abstract this, and as a result it will lead to the elimination, giving you double bond at this particular position. And because there is no anti hydrogen at this position, this product is not formed at all. So we will consider all the possibilities of eliminations, how they happen, how they cannot happen in the subsequent modules. And another thing that we will be looking in detail is that elimination often competes with substitution. When it happens, when it cannot happen, this also we will be considering in detail in subsequent modules.
The fourth type of organic reaction is rearrangement reaction. Molecular rearrangements involve migration of an atom or a group from one atom to another in the same molecule. The rearrangement reactions proceed via the formation of a cation, anion, or radical. The 1,2 rearrangement, pericyclic reactions, and metathesis occur via rearrangement. For example, the Beckmann rearrangement of oximes to give amides is a rearrangement reaction. In this case, an alkyl or aryl group anti to hydroxyl group migrates to nitrogen, forming an amide as the rearranged product.
Let us now try to understand the rearrangement reactions with the help of Beckmann rearrangement. In this Beckmann rearrangement reaction, we start with oximes, and as you are aware that these will show geometrical isomerism. So if we start with this particular geometrical isomer where this OH is on the same side as this R dash, and when this is reacted with H plus, there will be formation of this OH2 plus which gets lost as water molecule, and as a result there will be electron deficiency at this nitrogen created, and to fulfill this 1,2 migration happens, and the alkyl group which is anti to the OH always rearranges or shifts, and never this particular one which is syn. It is so because there is no steric hindrance on this side, rather this water molecule is there, it is not lost. As it is being lost, simultaneous there is a shifting of this alkyl group. So that is the reason why that the R group will be migrating, which is anti to the OH. That is, if you look at the initial molecule, here is the positioning of OH, so this R will migrate and not this particular R. So let us see what happens further is that when this is reacted, this undergoes further rearrangement. We have the formation of now this carbocation, because the alkyl group has moved here, there will be formation of this carbocation, and from the medium this water will be again attacking at this carbon, and we have the formation of this, from which the deprotonation and subsequently you can see here the enolization happens, and we get the formation of the amide. So what you can notice is right from the beginning oxime, the C double bond NOH, which is this group, has got converted to CONH, where the out of these two R's, the R and R dash, the R which is anti to OH gets attached to the nitrogen in the product. And if this is applied on cyclic oximes, suppose we have this particular cyclohexanone oxime, and when this is reacted with acid, it is interesting to note, you can clearly see that these are the 5 carbons as CH2 group, and this one will be migrating on this side. So this gets detached from here, and in place of C double bond NOH, how you can write the product is, in place of C double bond NOH, you write CONH, and now you can put these substituent, these are the 5 carbons, and they can be joined here, 1, 2, 3, 4 and 5. So as a result you get this 7-member cyclic ring, which is caprolactam. So this is also the application of Beckmann rearrangement, and you are already aware this caprolactam is very useful. This on further polymerization yields nylon 6 as the polymer.
The fifth type of organic reactions are oxidation and reduction reaction. In its simplest sense, oxidation is defined as addition of oxygen or removal of hydrogen, while reduction is removal of oxygen and addition of hydrogen. During an oxidation or reduction, there is a change in oxidation state of an atom of the substrate molecule. Oxidation reaction of organic compounds involves the conversion of a functional group having lower oxidation state to a higher one. Reduction is the opposite. Carbon can exhibit oxidation states from -4 to +4 in its compounds. Based on the oxidation state of carbon, we can group the organic compounds having different functional groups as shown here. Conversion within a category will not be called oxidation or reduction, as there will be no change in oxidation state in the molecule. For example, conversion of an alcohol to aldehyde or ketone is an oxidation reaction, while the reverse will be reduction. In this module, you have learnt about the different types of organic reaction and their examples. The main type of organic reactions are substitution, addition, elimination, rearrangement, oxidation, and reduction reactions.